Hi everyone, this is the last video of this unit on conservation of momentum. The essential question is, how can conservation of momentum help us explain and predict the motion of colliding and exploding objects? The big idea with momentum, which you've seen before with different variables, is that momentum is conserved in closed systems. So the total momentum is always going to be constant if you can close off a set of objects from every other object in the universe. This means that if you add up all the momenta of each object in a system at one instant in time, it's going to be equal to the sum of the momenta of the same objects later. Now, the momentum of an individual object might change, but the system, the total, does not. Some common examples of when we use this law of conservation of momentum are in systems that involve collisions or explosions. I'm sure in your minds you're imagining big dramatic things, car crashes and planets crashing into other planets, and those are certainly examples of collisions and explosions. But collisions and explosions can happen at much smaller scales as well. For example, anytime like a football player catches a ball, that's a collision. And an explosion, when you're just walking, you're pushing off the ground, the physics of walking is exactly the same as the physics of a big bomb blowing up in the air, for example. So even though they have kind of a grand, scary title of collisions and explosions, the physics here is really, really useful and really, really applicable to almost every aspect of your daily life. When objects collide or explode, so picture any of the collisions or explosions we just talked about, the object's velocity will be changing. It might change in size, so you speed up or you slow down, or you could even change in direction. So maybe you're moving positive velocity before the collision and negative velocity after. Because of our equation, P equals m times v, if our velocity is changing, the momentum must be changing as well, because if the v value changes in that equation, the mass of an object is constant because mass is conserved, so momentum is going to be changing as well. But the law of conservation of momentum means that for every object that's gaining some momentum in a collision or explosion, another object must be losing an equal amount of momentum. And this is going to be something that's going to help you guys with your problem solving throughout this unit, realizing that whatever momentum some object gains, a different object must be losing. So let's see if we can just solve a relatively simple explosion problem here, just using our natural intuition. I've got two ice skaters. They have the same mass, m, and they're going to push off of each other. What's going to happen? Hopefully, if you take a second and think about it, you'll predict that one of those ice skaters is going to move forward with a positive velocity, the other ice skater is going to move backward with a negative velocity, and really those velocities should be equal to each other because the ice skaters have the same mass. So now that we sort of know what the answer is, let's see if we can figure out why this makes sense as far as conservation of momentum goes. So if I wanted to solve this problem, the first thing I would do is draw my before and after systems, realizing that in a closed system, the momentum is conserved from one moment of time to another, just like mass. So then I'll look inside my closed system and think about the individual objects. When those skaters started, they both had no momentum, and the reason they had no momentum is because they had no velocity. They had some mass, but any number times a zero velocity gives you zero, so momentum is zero. That means that the total momentum in this system before they explode off of each other is actually zero. What this means, of course, is that at every moment in time, that system of objects must have zero momentum as well. This is weird because we know that these ice skaters are going to move. How can those ice skaters have zero momentum as a system when they are individually moving? Well, the way they can have it is one ice skater has some amount of positive momentum. If the other ice skater has exactly the same amount of negative momentum, you add those guys together, you end up with zero. So this is how momentum can be conserved in an explosion, even when the objects look really different after the explosion than they did before. So how about a slightly more challenging example? What's going to happen when the big football player pushes off of the little girl? They're both wearing ice skates as well. We're doing that to avoid friction, which complicates these problems a little bit, but we can get to friction later on. So what's going to happen? Hopefully you'd predict that they're going to go in opposite directions again. The football player goes backwards, the little girl goes forward, but this time they don't go at the same velocities, right? That little girl is going to go flying forward with a large positive velocity, and the football player is going to move backwards at a very, very small negative velocity. Let's move into our systems thinking and see if we can explain why it has to be this way as far as conservation of momentum. So the reason we have to arrive at that solution is because although the objects in the system have different velocities when they're done exploding from each other, they will still have equal but opposite momenta, which means that we can conserve momentum, right? So that big football player still has 0 momentum because big mass times 0 is 0. The little girl has a 0 momentum because little mass times 0 is 0. So the total momentum in that system is 0, just like the equal-sized ice skaters were earlier. And that means that after the explosion, the total momentum has to be 0. But this time, this total momentum looks a little bit different for the individual objects, because the way that we can have the same amount of momentum for a football player and a little girl when they have very different masses is that they also have to have different velocities. That football player with a big mass has to have a small velocity when we're done, so that the little girl with a tiny mass and a large velocity can balance out. So we still have 0 total momentum, even though the objects have different velocities when we're done. We'll do a bunch of practice solving these kinds of problems mathematically in class, but I did want to introduce one tool called an MVP chart, which is a really useful tool for tracking momentum. So let's say we have some kind of, in this case I've got a collision going on. Those last ones were explosion problems, but this is a collision. In fact, they say that a long, long time ago, scientists have concluded that the way our moon was formed was with a big, massive planet almost the size of Mars hitting Earth. So that would be a really exciting collision to happen. At any rate, so we've got this little Mars-sized planet running into Earth. The moment before the collision happens, that's just the instant in time right before they collide in your My Before system. And then a couple minutes later, after the collision has occurred. So if I want to track the momentum in this system before and after the collision, I set up what's called an MVP chart. And the way the MVP chart works is on the left side, we've got the variables. So we've got M, which is mass, of course, V is velocity, and P is momentum. And then I'm going to leave a column for each of the objects in the system. So before, I have Mars and Earth. I've got 2 columns. On the after side, I have the same 3 variables, MVP, but now I only have one object because they've smushed together into a single object. And that object's going to be called, well, I'm going to call it Mars Earth because it's those 2 things stuck together. So we'll do some, I'm not going to solve this problem out right now for you guys, we'll do it in class, but it's kind of like a Sudoku puzzle. You start filling in boxes, and as you fill in boxes, you start realizing that the values of the other boxes, you know, are determined by the ones that are already filled in. There's, you know, 3 rules, or there's really 2 rules for filling in these boxes. Mass is conserved. That means my Mars mass and Earth mass before must be equal to Mars Earth after, okay, because of conservation of mass. And momentum is conserved. So the momentum of the Mars plus the momentum of the Earth have to be equal to the momentum of the Mars Earth when we're done. So those are the 2 big rules. A quick note, because there is a 3rd variable in there, velocity. Velocity is not conserved. You cannot just assume that you add up the velocity of Mars and Earth before to equal the velocity after. And there's some good reasons that it doesn't work that way, which we'll talk about in a minute, but I did just want to be clear that when you're doing that table, remember that the only 2 things that are conserved are mass and momentum, not velocity. Before we end this video, I thought I'd talk just for a minute about why velocity isn't conserved. We know that objects change their velocity during a collision or explosion. And when those collisions and explosions happen, littler objects have to change velocity more than big objects. We saw this in the football player, little girl, ice skater example, right? The football player changed velocity a little bit, and the little girl changed a whole lot. So if you imagine like a scenario of a big and tiny object colliding, like a bug who's flying at -60 directly at a bus who's also moving at +60, if velocity was conserved, that would mean they'd stop, okay? But obviously they're not going to stop. What's going to happen is the bus's velocity is going to change a tiny bit. It might slow down a little bit because it ran into that bug, a change of -1, and the bug's velocity is going to really change a lot, right? It's going to go from -60 to +60 because it's stuck to the bus now, so it changes by 120. So all in all, you know, the velocity value should make sense to you. It should be logical to you, but they're definitely not going to be conserved from before to after. And one more little relationship that you will be using a lot when we do these collisions and explosions. Mass is going to have an inverse relationship with delta V, not V, but delta V, during a collision and explosion. That means the bigger the mass, the smaller the change in velocity, and the smaller the mass, the bigger the change in velocity during a collision or explosion. So please take a few minutes to summarize this video. How can conservation of momentum help us explain and predict the motion of colliding and exploding objects? And don't forget to try the graphic organizer and the extension questions to help you feel more confident with this material. Thank you.